Japan's new fusion reactor JT60SA, which confines a heated plasma in a donut-shaped chamber using superconducting magnets, has been successfully turned on. It is the largest and most sophisticated reactor in the world and supports the International Thermonuclear Experimental Reactor (ITER) project in France, studying the physics of fusion energy. On October 26, 2023, the first plasma was produced following almost 15 years of development and testing, demonstrating to the world that the apparatus performs its intended function, stated Fusion for Energy project manager Sam Davis. Recording JT60SA and related activities, this EU institution works with the National Institutes for Quantum Science and Technology, QEST, in Japan. The process by which two light atomic nuclei fuse together to form one heavier one while releasing a tremendous amount of energy is known as nuclear fusion. Fusion reactions occur in a state of matter known as plasma, a hot charged gas composed of free-moving electrons and positive ions, different from solids, liquids, and gases. This process powers the Sun and all other stars. Nuclei in our Sun must clash at temperatures as high as 10 million degrees Celsius to fuse, having enough energy from the high temperature to overcome their electrical repulsion. Once close, the attractive nuclear force between the nuclei will overcome the repulsion, and the nuclei must be contained in a tiny area to increase the chance of collision. Fusion occurs in the Sun due to intense pressure caused by its immense gravity. Why are scientists researching fusion energy? In a 1925 publication, British scientist Arthur Eddington proposed the theory that stars like our Sun are fueled by fusion reactions, combining hydrogen nuclei to generate helium. By the 1950s, scientists began exploring how humans could harness this process to produce significant amounts of energy. A fusion power plant wouldn't produce much radioactive waste, unlike conventional nuclear reactors using fission reactions, where uranium atoms are split. 1 gram of hydrogen isotopes needed for a fusion reaction could produce as much energy as 11 tons of coal. Since the discovery of nuclear fusion theory, scientists and engineers have worked to replicate and utilize it, as fusion has the potential to supply nearly infinite amounts of safe, economical, and clean energy to meet global demand if it can be duplicated on Earth at an industrial scale. Compared to fission, fusion has the potential to produce 4 times more energy per kilogram of fuel and about 4 million times more energy than burning coal or oil. Most fusion reactor designs under development will use a combination of tritium and deuterium, hydrogen atoms with additional neutrons. Theoretically, a few grams of these reactants could generate enough energy to power one person in a developed nation for 6 years. Fusion fuel is abundant and readily available. Tritium can be produced by the reaction of fusion-generated neutrons with naturally occurring lithium, while deuterium can be collected from seawater. These fuel reserves would last millions of years. Furthermore, it is not expected that future fusion reactors will produce high-activity or persistent radioactive waste. Fusion reactors are inherently safe. In the event of an accident or system failure, the plasma will quickly lose its energy and extinguish before causing sustained damage. This eliminates the risk of a runaway reaction or meltdown since the fusion process is difficult to start and maintain. Importantly, neither nuclear fusion nor fission produces greenhouse gases. Starting in the second half of this century, nuclear fusion may provide a reliable supply of low-carbon electricity. On Earth, to fuse deuterium and tritium, temperatures above 100 million degrees Celsius are needed. Magnetic forces and pressure must be controlled simultaneously to keep the plasma stable and sustain the fusion reaction long enough to produce more energy than was needed to start it. Although tests often achieve conditions similar to those needed for a fusion reactor, better confinement characteristics and plasma stability are required to continue the reaction and generate energy. Scientists and engineers worldwide are constantly designing new systems and materials to create net fusion energy. More than 50 countries conduct research on nuclear fusion and plasma physics. Recently, scientists accomplished scientific energy gain in a fusion experiment for the first time. Experts have developed many designs, such as tokamaks and stellarators, as well as methods using sophisticated fuels, lasers, and linear devices. The successful implementation of fusion energy will depend on how quickly the industry can develop, validate, and qualify fusion technologies, and how well international alliances can mobilize resources. Developing the necessary nuclear infrastructure, including standards, procedures, and best practices for this future energy source, is equally important. JT60SA. What is it? Unlike other large tokamaks, the reactor is designed to heat plasma to 200 million degrees Celsius and hold it for about 100 seconds. This will allow scientists to explore ways to regulate and enhance plasma performance and stability, which are essential for generating fusion power. JT60SA will support ITER, the massive international fusion reactor under construction in France, proving that fusion energy can produce more energy than it consumes. ITER will rely on operational expertise and technology that JT60SA will verify and test. Japan was allowed to build JT60SA and 2 smaller fusion facilities in exchange for France hosting ITER, the largest fusion experiment in history. This was part of a 2007 deal between the EU and Japan, which included modernizing Japan's aging JT60 reactor, operational since the mid-1980s. The cost of the reactor's complete rebuild was kept secret. JT60SA, roughly half as tall as ITER, can hold 135 cubic meters of plasma, about 1/6 of ITER's capacity. Alberto Loarte, head of ITER's science division, said that data from JT60SA plasmas would benefit ITER. The reactor took longer than expected to complete, over 15 years according to science.org. It was originally set to launch in 2016, but faced delays due to procurement issues and had to be redesigned after the March 2011 Tohoku earthquake. Then, during testing in March 2021, a major issue arose. A short circuit in the cable of one superconducting magnetic coil destroyed electrical connections and caused a helium leak that could have affected the cooling systems. The incident occurred when the circuit's current was at its lowest, and QEST project manager Hoshiori stated that severe damage could have happened if the current had been higher. It took 2.5 years to redesign insulation in over 100 electrical connections for safety. The incident also prompted ITER developers to plan more thorough testing of their coils. The disadvantage of JT60SA is that it will only use hydrogen and its isotope deuterium rather than tritium, a more powerful but also more expensive, scarce, and radioactive form of hydrogen. Since tritium is the preferred fuel for generating electricity, ITER will use deuterium-tritium starting in 2035. Japan also plans to build DEMO by 2050, a power station linking fusion energy commercialization and JT60SA and ITER research. Hoshiori expressed excitement about new privately funded fusion energy techniques, stating openness to collaboration with innovators. He noted it's great that more people are